Right. Joining me now is Dubi Lever from Gilat Satellite Networks. Dubi joined Gilat in 1997, beginning as a design review engineer specializing in hardware, radio frequency, FPGA, and communications algorithms. And he is currently a Group Chief Technology Officer. He holds 5 patents, is focused in recent years on NGSO, non-geostationary orbit constellations, and the migration of ground segment to cloud platforms and efficiency improvements to waveform. So welcome, Dubi. Thanks for joining us. Really good to have you here again on one of our programs. Now, let me start by Gilat is one of the leading satellite network providers, offering solutions for cellular backhauling, in-flight connectivity, enterprise, consumer, and defense applications. In our session today, we're going to be addressing mobility. So let me start by asking, what are the unique features that are needed to support mobility?
Okay, first of all, hi, Paul, audience. Thank you for inviting. Good to be back again. So indeed, so mobility. So there are several elements that are unique about mobility, and I'll run through them quickly. So I would say that one of the most important elements is handovers. Okay, when you have a terminal that's actually moving on the ground, it moves between the coverage of different beams of satellites, and even moves between different satellites. What is needed for that is to have a set of rules to determine how actually a terminal moves from one beam to another, from one satellite from another, and the customers demand a great deal of flexibility there. So there are many different criteria, and you have to have the ability to tweak it. So it can be based, for example, on some brute force, for example, based on a map, a predefined map. So when you cross a certain coordinate, then you know that you have to switch another beam. And it can be based on SNR, on signal to noise ratio estimations. It could be even, there's another element that can be taken into account is, for example, is load balancing. So you can decide to move from one beam to another based on the load between the beams. So this is related to handovers. Then something else that is often found that has is of high importance in mobility is the fact that you have normally antennas that you have to have a unique API for control these antennas. When you're looking at ground installations, fixed installations, normally you have simple antennas and boxes. There's not much control between them. When you're on a moving platform, you have to actually control the antenna. And for this control, you have to have, you typically use standards. For example, there's a standard called Open AMIP for the antenna or Open BMIP for the amplifiers. And the modem has to control the antenna. So using this standard, Open AMIP is something that is mandatory normally for mobility. And what's relatively new is on the data. So today, the typical interface would be an L-band analog interface, but what we are looking at, looking into the future, is having a digital interface. And here again, there's a standard that's supporting that. It's called DIFI, the Digital Interface Forum. And so standards for the interface between the modem and the antenna is also critical for mobility. Now, we have terminals that are moving, and the operators typically, they want to see them on the map. So you have to have within the NMS, the network management system, you have to have support of maps, which means you have to show, you have to have the ability to show real time where the terminal is on the map. You want to have the ability to even trace and maybe look historically and look for different points on the map, what are the telemetry. So we have a very rich feature set that has been designed around the map support. Now, where do we typically find terminals, mobile terminals? So we find them on vessels. It can be on aircrafts. It can be on trains, on buses. What we find in a large number of these terminals is the demand for very high bit rates and very high processing power. So this is really, the most powerful modems really in the industry today are probably for cruise ships. That's where you see the highest demand. There's insatiable demand for bandwidth there. Anything you can supply will be consumed. So generally speaking, there is a need for very high-end terminals for mobility platforms. Also, in terms of the bit rates and in terms of the processing power, the packets per seconds that are needed. And maybe just, I can talk about this forever. Just maybe the last one, which is not the last but not the least, is the fact that today, in the era where we have not only geo constellations but non-geostationary constellations as well, there's a need to be able to support both simultaneously, to have a multi-orbit support. Now, this has a degree of complexity because you have to have the ability, when you're in a mobile system, to power up in any beam at any given time and be able to connect, which is not a trivial challenge. This booting up process, once you're online, once you're connected, so moving between a beam, between a satellite is easily managed. But the fact that you can wake up anywhere in the world, when in the background it's possible that some of the parameters of the system have changed, so this is a challenge. So being able to support multi-orbit is another challenge. So these are really the points that I wanted to cover, Paul, related to mobility.
Okay, sure. Now, mobility services over satellite was initially offered over MSS. Now, with the soaring requirement for high rate solutions, which were introduced over FSS, and that led to the development of tracking antennas. Now, these antennas initially developed for FSS are now being adopted for NGSO, yet it seems that electronically steered arrays seem to be the leading solution. Is there still room in the satellite industry for mechanically steered antennas?
Okay, so let's put it this way. First of all, within Gilat, we're extremely familiar with all of this technology. We have all of the technologies in-house. We have panel antennas, we have parabolic antennas, which are mechanically steered, and we have electronically steerable arrays, which is we've already demonstrated over LEO constellation, airborne. So we're very much familiar with this, and we see the demands coming from the industry, and we understand how to ideally map it per application. Now, indeed, the ESES is the hottest topic in the industry. Everyone wants electronically steerable arrays. And the advantages are clear, okay? If we look at airborne applications, the ESA has a very low profile. And when you have a low profile, it can dramatically reduce the drag. And by doing so, you consume less fuel. We had a funded project in Europe with Clean Sky, which we did with Airbus. The whole idea was there really to promote technologies that are considered green technologies, and ESA can do the job. From that point of view, it's a very low profile antenna, and indeed it reduces the drag. Now, if we look at all the NGSO constellations, mainly the LEO constellations, so you can see that the majority of the constellations are looking indeed at electronically steerable arrays, because the satellites are moving at a rather rapid speed, and every several minutes you have to switch from one satellite to another satellite. So you have to have very fast steering. Doing fast steering mechanically is extremely challenging, especially if you think about the NTBF. Okay, if it has to work over years and all the time it's doing these rapid switches, you want to have a solution that's fast and also of very high reliability. And if the switching is sufficiently fast, you can even manage with a single antenna, because the steering is so fast that perhaps the disconnect would be like a small blip. You wouldn't even notice it. So it's important for LEO. And another advantage of ESA is for multi-beam. With some of the technologies, especially with digital electronically steerable arrays, you can easily generate a large number of beams. So if you want to have beams, you want to simultaneously look at different satellites, or you want to establish a new link before you drop the link. Okay, as the satellite is moving by, before you lose the line of sight of the satellite, you want to pick up the connectivity with the new satellite. So the ability to generate multiple beams is an advantage. Now, the whole question was really based on the fact: is there a future for panels? For sure, there's a need for panel antennas, and the reason is the following: that the ESA technology typically consumes much more power. Okay, the power consumption is higher. And the thing is that there are some of the platforms that are the main candidates for these antennas are very sensitive to the power that's needed. So if you look, for example, at the UAV, which is limited power, or maybe business aviation, you're not connected to the mains. Okay, you're based on the battery, and also you have sometimes challenges of heat dissipation under the radar. So there, the ESA can be challenging, and often the selection is for a panel antenna with an amplifier, simply because it consumes less power. Another challenge is the elevation. Okay, when you have a flat antenna, so when you're looking at boresight, which means that you're looking at a satellite that's maybe is perpendicular to the antenna, then you have the best performance. But as the elevation angle is reduced, the effective aperture gets lower and lower. And if you look at geosystems that sometimes want to work down to 10 degrees elevation, sometimes even less, and some of the NGSO, the non-geo constellations, 15, 20 degrees. So when you get so low, the effective aperture is really reduced dramatically. You can lose 6 or 7 dB, which is dramatic. And then what it means to compensate for that, you want to have a large antenna, higher power consumption, higher cost, whatsoever. So anywhere that you need low elevation, so for sure the panels have a compelling advantage. Then for some of the ESA technologies, there are also challenges related to the environment. Okay, there's some new technologies, let's say passive technologies, passive ESA, where it's still to be determined how it can really cope with the environmental challenges, especially in airborne. These are the main points that I wanted to highlight. Okay.
Now, virtualization is a hot topic in satellite networks. And I remember we discussed this in a previous program that we ran. How would you define the necessity for virtualization specifically in the mobility sector?
Okay, so I'll split it to two. We've got the modems and we've got the gateways. So from the modem, I mean, a virtualized platform would be ideal, because let's say if we take the connectivity to aircraft, in-flight connectivity. So you've got an aircraft that's flying, and potentially you'd want it maybe to roam between different providers. Okay, maybe one satellite operator or service provider has a coverage in one region, and you want to move to another region where maybe there's another satellite provider that maybe has more capacity or has maybe a better service, or it's more compelling. So from the aircraft, from the airline, and from their point of view, they would want to be very flexible in roaming between. So the advantages are clear. Mm-hmm. Okay, you have a virtualized platform where you can maybe load different images of the different vendors. Where it gets a bit tricky is that to have something that's fully flexible is challenging, because the constraints on the modem in terms of power consumption are extremely, extremely stringent. Okay, there's a standard called ARINC 791 anyway, but when we're looking at recent RFPs, we're seeing that the specific allocation for power consumption of modems is constantly being reduced. So you have to have something that extremely, as low as, that has to be as low power as possible. And another thing is that we're seeing also some crunching on the prices as well. Okay, it's not the early days of IFC where you could sell an antenna for many hundreds of thousands of dollars, and the installation is also very expensive. Prices are coming down, so you have to have something that's cost effective and also effective in terms of power consumption. So going for a full software defined radio, okay, which is based on FPGAs and lots of A2Ds, analog to digital converters, and digital to analog converters. They're also very expensive, and they're also very high on the power consumption, because with the new satellites, we're looking at very high symbol rates. Okay, so whereas in the past, in the older generation of satellites, where you had transponders maybe of 36 megahertz, now we're looking at satellites with beams of 500 megasymbols per second. And doing the signal processing at 500 megasymbols per second is extremely, extremely hungry on power consumption, and also the cost of the devices needed is very expensive. Mm-hmm. So what we have proposed in the past, because we've been involved in several initiatives to try and develop a universal modem. It's come from satellite operators, it's come from the aircraft industry. Our proposal for a universal modem would be a combination of maybe an ASIC for reception. After all, the DVB-S2X standard has been a tremendous success. It's been widely adopted in the industry, but many of the operators have taken ASIC for the DVB-S2X, but indeed to have the flexibility of the return channel on FPGA. And this is a wide common denominator in any case between the different hardware platforms of the different VSAT vendors. So this is regarding the modem. So yes, virtualized, still not fully flexible, not fully software defined, but to have some usage of ASICs as well. Regarding the gateway, so with the gateways, it makes also a great deal of sense, because when you have, if you look at the typical pattern of aircrafts, you see that it's like a wave. Okay, if you look at for example, the North Atlantic route, so the airplanes, they all fly roughly around the same hours. Okay, so you can see hours where there's a lot of traffic and at times where there's less traffic, which means that you have some gateways that at some hours they are working in a very excessive manner, okay, where they have to support a lot of aircrafts, and other times where maybe they're not as busy. So if you're going to pour lots of hardware into a single gateway, but you'll only be utilizing the hardware part of the time, it's not an efficient way to really use this hardware. So if you have a virtualized solution for the gateways, without going now into the whole big discussion about modem virtualization or the data processing, but generally as a concept, if you're virtualized, if you have a virtualized solution for the gateway, so you can, in a way, it's easier to ramp up or ramp down resources and shift them between different areas of the coverage.
Okay. Now, talking about the future, and it definitely looks bright. The current install base of satellite connectivity on aircrafts and vessels is still relatively low. NGSO and VHTS will bring down the service prices. Now, in terms of technology, what new solutions should we expect to see in the future?
Okay, so I think there are several aspects to that. I think that if you look at typical satellites used today for maybe GEO or non-GEO, use KU or KA. These are the typical bands that they use for the terminals. Okay, we are seeing an inclination to move to QV band for the gateways. Okay, because today you have to, the bottleneck really of a satellite today is the ability to aggregate all the traffic to a gateway, and you only have around 2.5 gigahertz on two polarizations for the KA. So if you want to have higher capacity on a satellite and you want to handle this bottleneck without adding too many gateway sites, so you can extend into the QV band. So this is good for the gateways. But then you ask yourself, why not go for QV for terminals? And the obvious answer is, well, you have the issue of the atmosphere and the environmental conditions, where you always have to take large margins for fading. But if you think about an aircraft, that the majority of the time it is really flying above the clouds, there's no reason why you shouldn't really have QV service for aircraft. So I think that we should see in the future migration to QV on the user side for aircraft. Okay, so this is one aspect. Another aspect, I think, is the holy grail of the electronically steerable arrays, which is the multi-band. Okay, if you look at classic panel antennas, so there's like Viasat have such an antenna, Gilat have, and others have an antenna where it's KU and KA. So you have basically two panels on a rotating pedestal. One is KU, one is KA, and that way you can roam between satellites of KU, KA. On ESA, it's more challenging here because you're designing elements that are spaced according to the wavelength of a specific band. So you can have multiple apertures, but that would take up a lot of space. So sort of like the holy grail is to have a single ESA that can support maybe both KU and KA transmit and receive, but maybe in the future higher bands. So this is a very interesting area where I expect to see innovation in the aperture design, how to maybe interlace KU, KA. It's another interesting. And the last aspect I would like to refer to is the fact that we're seeing a new generation of satellites coming out, which are software-defined satellites, that they have the ability to generate a large number of beams digitally. So they have digital beamforming. And what this really is creating, it's creating a whole new pattern, a whole new model for connecting to mobile platforms, because these satellites have the ability to actually track vessels or track aircraft. Now, such technology has been available. There have been steerable antennas in the past, mechanically steered, but it was at a very low volume. So you could only track a very small number of vessels. In the future, with the ability to track hundreds or even thousands of vessels, we think that this is going to change the whole way of how the service is granted to moving platforms.
Okay, good. Just one last question. You've mentioned in-flight connectivity. I think you mentioned earlier cruise vessels, which is interesting because later on in the program, I've got a conversation similar to the one we're having now with Bernard Andrade from Silver Sea Cruises, and that is a really it featured on an earlier program, but it seemed contextual for this program, so I'm going to run that again. Let me ask you. You haven't actually mentioned surface mobility, road and rail, and I was wondering where Gilat stands with that, and if you have an interest in that. I would imagine you do, and how long do you think it will be before we see a satellite play on road and rail?
Okay, so we have to relate to every segment separately. Okay, so let's start with rail. Rail has had lots of ups and downs. We've sold in the past to several in several different countries, with several different customers. The thing with rails is that there's the inclination to add terrestrial infrastructure. So when you have these larger corporates that are laying down even new rails, they often lay down the infrastructure as well. So it can be fibers along the rails, and it can be full cellular coverage around along the rails. So I think this is the sort of thing that's maybe in a way limiting maybe larger investments into satellite for rails, and it's yet to be seen. There may be some more opportunities in the future, but I think that because we're seeing a lot of investment in terrestrial infrastructure along the rails, that there may be more opportunities in the future, but we see this like going up and down all the time. So this is rails. Regarding road, so obviously it's essential for like homeland security and for defense. That's a big market, and that's needed. Beyond that, I remember reading maybe last year Elon Musk declaring that he has no intention of putting his Starlink constellation on his Tesla cars. Mm-hmm. So when we're looking at cars, it's a bit complicated because you have to understand that there are different applications in the car. So, for example, you've got the media. So media is extremely high bandwidth. So to support that over satellite is problematic. So you have to have a relatively large antenna to support that bit rate. So that's a bit, the capacity will be expensive, the antenna will be expensive. Not sure that it meets the business model. Then if you're looking at something very minimal of just, let's say, a heartbeat of the driver, like health and that, see, they need very low bit rate. And for that, indeed, you can go to the classical solutions like sort of infrastructure you have today on satellites for asset tracking, like relatively low rate information that's needed. The question is if there will eventually be a new business case for something more intermediate, and there we might see some more interesting applications. So just to summarize, I mean, for connected cars, it very much depends what you're looking at for what connectivity. I think media won't happen so much. On the very low bit rates, there are really relatively cheap available solutions today based on L-band with a small and cheap antenna. And will there be a business case for something in the middle? It's yet to be seen. Okay,
interesting. Dubi Lever, CTO, Gilat Satellite Networks, always a pleasure, and thank you very much for contributing your erudition to this program. And with that, have a very good evening. I look forward to running this on Thursday.
Excellent. Thank you very much, Paul.
All right.